Hi everyone. Today I'm excited to tell you about my work on the deployment of indium aluminum nitride, gallium nitride Hall effect sensors for bucket transformer monitoring and forecasting. This work was completed at Stanford's Extreme Environment Microsystems Laboratory, XLab, in collaboration with Prolec GE. Transformer cores produce powerful AC magnetic fields, which can be used to monitor transformer health and performance. However, the inside of a bucket transformer is a harsh environment for sensors. Temperatures reach as high as 140 Celsius, and shorts can produce magnetic flux of 2.5 Tesla for 3 seconds. Normal field strength is highly variable, between 5 and 300 millitesla. In order to capture meaningful data, sensors in the bucket must have resolution better than 5 millitesla, while remaining unaffected by temperature or very high flux. In our lab, Hannah Alpert et al. Demonstrated the promise of InAlN sensor recovery for temperatures as high as 600 Celsius. Our plan was to mount these sensors onto sensor tester boards, STBs, that had an onboard analog to digital converter. Data was sent from the STB to a microcontroller mounted outside the transformer, where data was stored on a micro SD card. The measured Hall voltage is directly related to the magnetic field strength and therefore the current inside the transformer. Hall effect sensors have a great deal of potential for use in transformers because they are low cost, easy to integrate, and linear over a wide range of magnetic fields. A Hall sensor is a thin piece of p-type semiconductor positioned orthogonal to the magnetic field the user wishes to measure. It is constructed with 4 metal pads arranged in a diamond pattern around the semiconductor. A known current is run through the semiconductor across opposite pads, which generates a flow of electrons across the middle. The magnetic field bends some of these electrons toward one side of the semiconductor, causing a charge imbalance. That charge imbalance is measured as a voltage called V Hall and is directly related to the perpendicular magnetic field strength. So here's a closer look at the sensor and STB. 4 InAlN wide bandgap Hall sensors were printed on 2.5 by 2.5 millimeter die. After probing one of these sensors to confirm that it had no shorts, each of the sensor's 4 pads were wire bonded to the STB. These STBs were printed on a PCB with 180 C glass transition temperature to ensure the high temperatures in the transformer wouldn't affect it. Now, to test these individual sensors, independent of the STB, we used the LakeShore 8404 Hall measurement system, capable of a wide range of temperatures and fields over 1.5 Tesla. Here's our die, which is taped onto this small pad and then pinned here. Now, this is mounted down between these 2 very large magnets, the big blue cylinders here. While of course the LakeShore cannot simulate a transformer, it was able to tell us how these sensors themselves would perform under thermal and high magnetic field stresses. So here we ranged the applied field from minus 500 to 500 millitesla with a 5 millitesla step size, recording the measured Hall voltage. Hall voltages were not averaged, so what you're seeing here is raw sensor output. The slope of this line tells us the sensitivity of this particular sensor, which can vary based on any manufacturing defects. Taking 5 millitesla steps, we see a very clean, linear relationship. Any flattening at the edges would indicate sensor saturation, but we don't see any of that. This linear relationship also indicates that the sensor's resolution is at least 5 millitesla. But we really needed to make sure that resolution was low. So to ensure that, we then swept from minus 20 to 20 millitesla with a step size of only 0.1 millitesla or 1 Gauss. Again, we see perfect linearity between applied field and measured Hall voltage, so we concluded that our resolution would certainly be better than 5 millitesla. Now, once again, using the LakeShore, we examined sensitivity across a range of temperatures, from 30 to 150 Celsius. Now, each of the points you see on this chart represents the sensitivity measured by sweeping the field from minus 20 to 20 millitesla, like we just saw on the previous slide, at the respective temperature. While there does seem to be some upwards trend in sensitivity, as temperature increases, its magnitude is so low that it's very unlikely to affect any measurements taken in the field. The offset shows even less response to temperature with no clear trends and changes on the order of 1 Gauss. Now, after mounting these sensors to STBs, we needed to see if their sensitivity or offset was permanently or even temporarily affected after being exposed to an extremely high magnetic flux. Prolec GE suggested that a short in one of their transformers could generate a 2.5 Tesla field for 3 seconds. So we exposed our sensors to a 3 Tesla field for 5 seconds by placing them in an MRI's B0 field. Now here you're seeing current bias sensitivity, which accounts for the current we fed the Hall sensors. We measured sensitivity using a Helmholtz coil set up in our lab. Sensitivity and offset, as we can see here, had no major changes, and the small variations we do see fall within the bounds of experimental error. So, knowing that our sensors could stand up to these major environmental challenges, we designed and built a simple prototype that could record data from multiple sensors. What you see here is the front end, with a plug-in for the SAM32 microcontroller on the left and up to 6 sensors on the right. Each sensor communicates with the microcontroller using SPI interface, so 7 wires run from each STB. Now here's a look at the other side of what we just saw. This is the back end, where the daisy chaining of sensors has been put together. Ideally, this would actually be done inside the transformer, and I'll elaborate on that point a bit more in the future work section. So here's a look at the fully assembled prototype. The SAM32 microcontroller is mounted and connected in this picture to 2 sensors. I would like to point out that the wiring used here is very basic and indicative of this prototype's proof of concept role. In a real transformer, these wires would have to be much tougher and able to withstand high temperatures and submersion in hot mineral oil for decades. The sensor network is powered by a 3.7 volt LiPo battery and can run up to 6 sensors at once. Now here's a sample of the data collected from 2 sensors oriented around a dry bucket transformer at Prolec GE. These sensors were not submerged in mineral oil during data collection, just around a dry transformer. Their constant offsets have been removed, just as they would have been in the field. The 2 sensors operate both here at roughly 1.3 kilohertz, which unfortunately is far lower than Prolec GE would require in a real transformer. So while our sensors have proved themselves, unfortunately the microcontroller we used was not powerful enough to run multiple sensors at 6 kilohertz, which was the requirement Prolec would have for an in-field transformer. So in conclusion, our InAlN GaN sensors held up. They had no issues with temperatures up to 150 Celsius, and magnetic fluxes of 3 Tesla had no effect. The sensors maintained better than needed resolution, and the STBs survived in mineral oil after receiving an epoxy coating. The final prototype collected data from up to 6 sensors, but the microcontroller was unable to provide a high enough sampling rate to be considered in real-world transformer monitoring. More broadly speaking, though, this work really demonstrates the ability to utilize embedded magnetic field sensors to monitor, diagnose, and even forecast electrical grid system health and performance via IoT platforms. A better version of this prototype could reduce upkeep costs and improve reliability across the industrial power sector. So now let's talk about future work, which I really think is the most important part of this project, since I really see this as a first step in the right direction. So like we just talked about, a more powerful microcontroller is going to be needed to run these sensors at 6 kilohertz. We chose the SAM32 for its reliability in the past and the familiarity we had with it in our lab. I mentioned earlier daisy chaining should be done inside the transformer, and that's because we want as few wires going through the wall of the bucket as possible. In this prototype, each sensor required 7 wires, so a total of 42 through the bucket for 6 sensors. Now, using SPI interface, each sensor must have its own chip select and data ready line, but everything else can be shared. So daisy chaining inside the transformer would mean there's only 17 lines rather than 42 going through the bucket wall for 6 sensors. Our lab chose to investigate indium aluminum nitride, gallium nitride sensors in particular because they had proven themselves durable and reliable in our lab's previous work. Because silicon Hall sensors fail around 200 Celsius, I do think that future work with transformers should include some more simple off-the-shelf silicon sensors. If they can withstand the heat as well as the magnetic flux from shorts, then they would be potentially a cheaper option, or at least a more readily available option. So I mentioned earlier, the wiring would have to be upgraded to survive within the oil of a transformer, but of course that's a step we did not take since we only conducted tests on dry transformers. Now, while this proof of concept ran on a 3.7 volt LiPo, I would suggest that its extremely low power usage could probably be kept up by a small solar panel mounted on the outside of the transformer. And finally, taking a pretty long step past the scope of this project, I think it'll be important to answer some larger integrated systems questions about how to collect and relay relevant data from every transformer in a large network. With more than half a dozen sensors in each transformer, that is a huge amount of data to work with. And while it's outside of my experience, this is a problem that is going to have to be approached by power companies with a more intimate understanding of their own systems and operations. So a huge thanks to all the fantastic people at XLab, to Prolec GE and our other funding sources, as well as to the great folks around Stanford who contributed to this project. So thank you so much. It was an honor to present today. I hope that I will teach you something, as I am so excited to learn so much at this conference. So thank you for your time, and I hope you stay safe and well.